Okay, so now we're going to look at, well, how do these electron configurations and electronic structure, right? Where did I put the pen? How do those give us the properties of the elements themselves, right? And so these are important for the chemical and physical properties, right? Chemical meaning how does it bond, interact with other electrons. Physical meaning things like hardness and things, hardness, conductivity. Those are all would all be considered physical properties of the materials themselves, right? So we said that the you know, protons gives the atom its identity. Electrons kind of give the atom its behavior, its personality, right? How does this interact with other atoms, right? So that's what the electrons tell us. That's why it's important to tell us, to understand how the electron configuration works, right? These things include things like atomic size, ionization energy, metallic character, and then one we're going to add today. We won't talk a whole lot about it until we get to molecules, is electronegativity too. And we'll talk in detail about what each of these represent. And so these properties are commonly known as periodic trends, right? So based off of where an element is on the periodic table, you'll be able to say something like, well, is francium bigger or smaller than rubidium? Is yttrium, more metallic or less metallic than molybdenum, and things like that. How do you know? Well, based off the periodic table, because it tells us about the electron structure of the atoms, that'll tell us things about these properties. In the way it's organized, we'll be able to determine these trends. All right, am I good to go on to the next one? Right, so the first one is atomic size, right? So as we go across a group from left to right, we decrease in size, right? So this is decreasing radius, which means decreasing size. Oops. As we go down periods, right? So from 1 to 5, we increase in size. All right, and so the reason that we decrease in size is because as we're going across groups, right? We're going from left to right, from column to column. We have the same relative size for the atomic shell. What does that mean? Well, that principal energy level gives us kind of the energy shell of the electrons on the outermost shell. The outermost shell is basically the size limit of our atom. As we go across a period, what can you say about the number of protons? As we go across groups, sorry, not a period. If we go from left to right, what happens to the atomic number within a period? They increase, right? Which means we're gaining what as we go across? Mass, and in the form of neutrons and protons, right? So as we increase protons, right, we have a larger charge on the nucleus. Why? Because we're adding positively charged things to the nucleus. So for this given size, or this outermost shell of the atoms, we have more positive charges in the center, right? So if, let's say we have n equals 1, and this is our relative size for hydrogen, right? Hydrogen has 1 positive charge and then 1 negative charge in its outermost shell. When we go to helium, right, we're still in the n equals 1 principal energy level, right? So this energy level that's represented by the wave of the electron is still occupying the same space, right, for helium, right? So the energy level is still at the same distance, except now we have 2 protons, right, and 2 electrons that exist within this kind of energy shell right there. Because we have the same kind of distance on this energy level, but the number of positive charges in the center has gone up, it contracts, right? So we have the kind of like where, you have like a soccer ball, and inside the soccer ball you have something that's pulling on the outside of the soccer ball. And if you add more of that stuff in the center for a given size soccer ball, it's gonna contract it more, right? It's gonna pull it inside more. And so the protons act like that because you have this given size for the S sublevel. As you add more protons for that S sublevel and whatever the principal energy level is, it contracts that outermost shell in more, right? So the size decreases as we go across the group. As we go down, right, what increases as we go down periods? We go from period 1 to 2 to 3 to 4. What does the period represent? The maximum principal energy level, right? So that means that we've filled in all these electrons, the core electrons. We go to the next principal energy level. Now we add another shell on top of that, right? So when we go up in principal energy levels, we get another electron shell, right? We think of it like an onion, right? One more outer shell increases the size, right? We go down another period, add another shell of an onion, or the electron shell increases in size. So that's why size goes up as we go down a period. Why? Because as we go down periods, or we increase the period number, we get more principal energy levels, right? Which means we get another shell added onto the atom, right? It's like when you make jawbreakers, right? You coat it in another layer of sugar. Okay, so that's how the atomic size. Summer?
So the atomic number is directly related to the energy principle?
The period number is related to the highest principal energy level in that atom, right? So if you look at rubidium, Rb, element number 37, that's in period 5, which means the highest principal energy level for that element is 5, right? So we think about it, that means you have 5 electron layers. And the outermost one is the 5th layer, right? And that's why it gets bigger, right? Every time you add a layer, we expand out a little bit more to fit all those extra electrons that are going to go in there. All right, any other questions on the size? All right, so those are trends for atomic size. The next one we have is ionization energy. And this is the energy required to remove an outer or valence electron from the atom in a gaseous state. Gaseous state, you don't really have to worry about that much. The reason is just because these things are measured in the gas phase. And so this is basically, if we think about what we did on Wednesday with the flame test, right? The flame test kind of looks at adding energy in the form of heat to remove an electron or excite an electron in these atoms, and then that'll emit light, right? Another way we can do this is if you hit it with a photon or a particle of light, how much energy that light has can ionize or kick off an electron from that atom. And so when an electron is removed from an atom, a cation, or an ion with a positive charge, is formed. All right, so if we have a reaction like this represented, we'll talk more about what reactions look like. This, we have a sodium atom. We hit it with some form of ionizing energy. In the end, you get a sodium atom with a positive charge. So this is our cation and our ionized electron. Right, and so does anyone know any other potential forms of energy that can be ionizing? Anything that's ionizing tends to be very bad for you. All right, so when you go to the dentist office and they hit you with x-rays, and they go stand behind the lead, right? The reason they use the lead is because it's a heavy element. It'll block a lot of the x-rays. But x-rays are strong enough that if they hit an electron in an atom in your body, it'll ionize. It'll kick off an electron. Now you have a charged little piece of DNA or something. That DNA reacts with something around it because it's charged now. That can, be very bad for that cell, right? So the cell will probably die if you ionize a lot of the molecules in there. Right, so ionizing energy is just how easy it is to just remove an electron. And so how does the ionizing energy behave based on periodic trends? Well, it decreases going down periods, right? So as we go down or increasing period, right, which just means we're going down the periodic table, the energy required to remove an electron becomes less. And why is that? Well, because if we look at each of these little diagrams here, here's a lithium atom, sodium, and potassium. Ionizing, again, refers to the outermost electrons that we're kicking off, right? As we go down periods, we said what happens to the atoms. What was the previous thing that we talked about?
The principal energy.
Yeah, the principal energy level goes up, which means what happens to the size of the atom? It gets bigger, right? And that means that electron is farther from the nucleus. The electron's negatively charged, it's attracted to the positive charge of the nucleus. As it gets farther away, it's not as attracted to the nucleus anymore because it's farther away, right? Just as you get two magnets, you kind of start to bring them closer, that you feel them a little bit, and they get close to each other and they snap together, right? The attraction gets stronger the closer it is. It's the same thing for an electron and nucleus, right? So if the atom is larger, it becomes easier to remove that outermost electron, right? As the atom gets larger, it is easier to remove the farthest electrons, right? As it gets farther away, this isn't as tightly bound to the nucleus anymore. It's easier to kind of flick it off. All right, so the ionizing energy decreases. It requires less energy to remove an electron, the bigger the atom, okay?
So if we say that the more you go down a group, it requires less energy, does that mean that the further you go down in the periodic table, the more radioactive you get as well?
You do get more radioactive as you go farther down in the periodic table, right? So if you look at the ones that are kind of not the filled, but just the outline of the letters, those are radioactive elements. But that has to do with the structure of the nucleus, right? So the nucleus is where radioactivity comes from. So it's beyond the world of just chemistry. It's dealing with the physics of how the nucleus is structured. So the same way that we have sublevels and energy levels for electrons in the atom, the nucleus has sublevels, energy levels for protons, neutrons, quarks, and whatnot in the nucleus of the atom. In those stabilities, when they decay or get excited, release more potent forms of radiation, right? In atoms, really the most dangerous type of energy that you'll get released will be from, if you use heavier elements, it will be like X-rays. So you can get that, but the X-rays is as far as you'll get there. Whereas uranium or something can emit a gamma ray, which is very, very ionizing. Yeah, good question. Okay. And then going across groups, right? So sodium, lithium, potassium, that's in group 1. Beryllium, magnesium, calcium, group 2. Right, we go across the periods, right, across the groups, the ionizing energy increases, right? So this right here, in case you can't read it, says increases. And that's because of the same thing that we said as you go across the group, the size generally gets a little bit smaller, right? That means that as you're adding in more protons for a given shell, we said the size gets smaller. The outermost electron is closer to the nucleus, so it's more tightly bound, right? The outermost electron, so atomic size decreases. We go from left to right. Across groups. And that means that the outer electrons are closer and require more energy to knock off, right? As the outermost atoms get closer to the nucleus, they require more energy to knock off. And so you see that there tends to be a general trend, right? But there's these little anomalies here. So these anomalies, actually, that's on the next slide, so I'll wait till you guys are done writing this. But right, so this idea here is just the same as the atomic size. The same argument we use for why it's easier for to ionize larger atoms is why it's harder to ionize smaller atoms. If we go from left to right, the atoms get smaller, right? So as we go from left to right, the atoms get smaller, which means it takes more ionization energy because it's higher on this axis to knock it off, right? So let's say this is 5 kilojoules or something. Fluorine requires 6 kilojoules because it's larger there. Yep, that means the outermost electrons are more tightly bound to that atom. That's exactly right. Okay, and then we see that we have these anomalies here. And so these anomalies, where they come from, is based off of half-filled or fully filled sublevels and orbitals. So let's look at an example. How many valence electrons does boron, aluminum, and galadrium have? 3, right? Because it's in group 3. That means that we have, and it's in what block? The P block, right? So this is in the P block. So if you got rid of 1 electron, how many valence electrons would it have? 2, which means that now you don't have 1 electron in the P block and 2 in the S block. Instead, you only have 1 full S orbital and then the 1 full S sublevel, and the P sublevel is completely empty. So because atoms like to be stable, right, instead of just having 1 electron in an orbital alone, it makes it easier to kind of get rid of that electron, just have a completely full S sublevel, right? So these have a full S sublevel. And because that is a very, very happy state, it makes it easier to ionize these elements because you hit it with some energy and then it just becomes a full S sublevel. All right, so this is a happy state. So if it can reach that, it'll do so more easily than, for example, carbon. You'd have to ionize 2 elements or 2 electrons to get there, right? To get to a full S sublevel, you have to ionize 2 of them. 2 electrons to get there. So because it's right next to, it's only 1 electron away, it makes it easier to ionize those atoms. Why? Because it becomes happy like beryllium and magnesium do. These elements, oxygen, sulfur, and what is that, selenium, right? Those are what? In group what? Those are in group 6, which means they have how many valence electrons? 6 valence electrons, right? So if they have 6 valence electrons, they have 2 in the S sublevel, and then they have 4 in the P sublevel. So write this, P, 4 electrons. Right, so it looks something like this, right, for each of these. Right, when we look at the orbital diagram for the P sublevel, so this is just a generic P sublevel, how do we fill in 4 electrons here? 1, where's the next electron go? The next orbital, and then the next orbital, And so that's how 4 electrons fills in, right? We know we fill in each orbital first because that's how the electrons prefer. They prefer to be spaced out. Which means that if we were just to get rid of this 1 electron, this would be happy because it has a half-filled p sublevel. Whereas with the extra electron, it's like, okay, this kind of adds a little bit of imbalance now, right? One of these rooms is full and the other ones aren't. So it makes it easy to get rid of this electron because a half-filled p sublevel is also a happy, is what we would say is a happy state, or a low energy state. If we get rid of this with ionization energy, a half-filled p sublevel is a happy state or low energy state. So because it's having a half-filled p sublevel is low in energy, it makes it easy to get rid of that extra electron, which is why you see these anomalies as you go across for ionization energy. And so I drew out the orbital diagram there, but you can also look directly at the electron configuration, right? If we were to just get rid of this electron, you only have 3, that's half filled. For boron and beryllium, right? If I get rid of this 1 electron here, now I just have a full s sublevel, right? So this kind of anomalies as we go across in ionization energy are just due to facts of how we fill in electrons into their different sublevels, right? So if we remove one, it gives us a state that is relatively happy or low in energy. Okay, and then the last one is metallic character. Metallic character follows the same trend as atomic size, right? As we go down periods, the metallic character increases, and as we go from left to right across group, the metallic character decreases. Metallic character just means like shininess, conductivity, and also how easy it is for it to lose electrons. That's another thing that metals do. You can also remember this because you know group 1 and 2 are called the earth metals and the alkali earth metals, right? And then the group 3 through 8, those are our main group elements, right? So, and then also the D block, everything in between are called the transition metals, right? So those are all the metals, right? They have metal in their name and the other ones don't. That's another way that you can remember metallic character. Okay, so we'll stop there for now. Another thing that I'll mention right now, just because we're here, is that the electronegativity, which we won't get to until Wednesday, the electronegativity follows the same trend as the ionization energy, right? In electronegativity, that's just going to be how much that atom wants to pull electrons to itself. So it makes more sense in the term when we talk about covalent bonds, but how likely is that atom to then pull things to itself? So what that means is something like fluorine, for example, is going to pull electrons very hard, where something like sodium will not pull electrons at all. And we'll talk more about that. It'll make more sense once we talk about that in the context of bonding. On its own, you think of it more as ionization energy. When it's in a bond, you think of it more as electronegativity. All right, so that'll